Have you ever pondered the uniqueness of prime numbers and their role in the universe of mathematics? They're the building blocks, the atoms if you will, of the number system. They're like the chemical elements, each with its own distinct properties, that combine to form the complex world of numbers that we navigate every day. These are the prime numbers, the natural numbers greater than 1 that have only 2 positive divisors, 1 and themselves. The solitary figures that can't be divided into smaller integers without leaving a remainder. They're fascinating, puzzling, and sometimes downright elusive. In this video, we're going to delve deep into the intriguing realm of prime numbers. We'll explore their definition, their properties, and the fundamental theorem of arithmetic that involves them. We'll sift through the ancient Sieve of Eratosthenes, count them using Chebyshev's pi function, and marvel at their twins. We'll also discuss their application in modern cryptography, so buckle up for a fun-filled journey into the world of prime numbers. Prime numbers in their simplest form are natural numbers greater than 1 with only 2 positive divisors, 1 and the number itself. Dive into the world of prime numbers with us, and let's explore their unique and fascinating properties. At its core, a prime number is a natural number that holds 2 distinct positive divisors. These divisors are 1 and the number itself. The number 2, for instance, is a prime number because it can only be divided evenly by 1 and 2. Now you might be wondering, why is 1 not considered a prime number? Well, the definition of a prime number requires it to have exactly 2 distinct positive divisors, and 1 only has 1 divisor, which is 1 itself. Moving on, let's talk about the uniqueness of prime numbers. Each prime number is unique in that it cannot be produced by multiplying 2 smaller natural numbers together. This property sets them apart from composite numbers, which can be factored into smaller integers. In the realm of mathematics, prime numbers hold a special place. They are the atoms of arithmetic, the building blocks of the natural numbers. This is beautifully encapsulated in the fundamental theorem of arithmetic, which states that every natural number greater than 1 is either a prime number itself, or can be factored as a unique product of prime numbers, regardless of the order of the factors. In other words, just as atoms combine in various ways to form molecules that make up the physical world, prime numbers combine to form all other natural numbers. This highlights the central role that these unique numbers play in our number system. The world of prime numbers is filled with mystery and intrigue. Despite being so simple in definition, prime numbers have properties and patterns that mathematicians are still trying to fully understand. They are an integral part of number theory, an area of mathematics dedicated to studying properties and relationships of numbers. So, in essence, prime numbers are the building blocks of all natural numbers. Now imagine you have a tool to find all prime numbers less than a given integer. This brings us to the Sieve of Eratosthenes, a method as ancient as it is ingenious. Named after the Greek mathematician Eratosthenes, this technique helps us unearth prime numbers with ease. Picture this. You have a list of numbers up to a certain limit. The first number is 2, the smallest prime number. You go through the list, crossing out every second number because they are divisible by 2, and therefore not prime. The next uncrossed number is 3, another prime. You repeat the process, crossing out every third number. You continue this pattern, each time moving to the next uncrossed number and eliminating its multiples. What you're left with is a list of numbers untouched by the sieve. And those, my friends, are your prime numbers. So with the Sieve of Eratosthenes, unearthing prime numbers becomes a piece of cake. Ever heard of twin primes? They are prime numbers with a difference of just 2 between them. Imagine 2 siblings standing side by side, separated by a mere 2 units on the number line. Examples of these pairs include 3 and 5, 11 and 13, or 17 and 19. But here's the real kicker. There's a conjecture, a mathematical proposition that's yet to be proven, named the twin prime conjecture. Proposed by the mathematician Alphonse de Polignac in the 19th century, this conjecture asserts that there are infinitely many pairs of twin primes. That's right, an infinite number of these sibling pairs. Despite numerous attempts, mathematicians have yet to confirm or refute this conjecture, making it one of the most tantalizing unsolved problems in number theory. So, the next time you come across a pair of primes with a difference of 2, remember, they could be part of an infinite family. The twin prime conjecture, although still unproven, is an intriguing aspect of prime number theory. Now let's delve into the prime number theorem, a key result in number theory. This theorem is a cornerstone in our understanding of prime numbers. It describes how these unique numbers are distributed among the positive integers. The theorem states that if we pick a random number, the chance that it is prime is roughly 1 divided by the natural logarithm of that number. In simpler terms, the larger the numbers we're dealing with, the less likely we are to stumble upon a prime. This makes prime numbers less common as numbers increase, but they never completely disappear no matter how far we venture into the number line. This theorem was a monumental achievement in mathematics, not just for its implications, but also for the mathematical techniques developed to prove it. It was a culmination of the efforts of many mathematicians, including Riemann, Chebyshev, and Gauss. The prime number theorem indeed offers a fascinating insight into the frequency of prime numbers. Scene script. Prime numbers can also take some unique forms like Mersenne primes and Fermat primes. Let's venture into the intriguing world of Mersenne primes first. Named after the French mathematician Marin Mersenne, these primes are of the form 2 raised to the power of a prime number, -1. That's 2 circumflex n, 1, where n itself is a prime number. Sounds simple, right? But the interesting part is, not all numbers of this form are prime. For instance, let's take n equals 11, a prime number. 2 raised to the power of 11 minus 1 equals 2047, which is not a prime number as it can be factored into 23 and 89. So, Mersenne primes are a bit elusive, making their discovery quite an exciting event. Now let's shift our focus to Fermat primes, named after Pierre de Fermat, another French mathematician. Fermat primes follow a different form. They are of the form 2 raised to the power of 2 raised to the power n plus 1. That's 2 circumflex n plus 1. Fermat conjectured that all numbers of this form are prime. However, this turned out not to be the case. Only the first 5 numbers that Fermat tested are prime. After that, all the Fermat numbers discovered so far are composite, not prime. So you see, Fermat primes are even rarer than Mersenne primes. These unusual primes, Mersenne and Fermat primes, add a unique flavor to the world of prime numbers. They tease us with their elegant forms and then surprise us by not always being prime. But that's the beauty of mathematics, isn't it? It's full of surprises and challenges, pushing us to explore and discover more. Mersenne and Fermat primes, though rare, add a unique flavor to the world of prime numbers. Did you know that prime numbers are fundamental to modern cryptography? Yes, these seemingly simple numbers play a huge role in keeping our digital world secure. In cryptography, prime numbers are used in integer factorization algorithms, such as the RSA algorithm. RSA, named after its creators Rivest, Shamir, and Edelman, is a public key crypto system widely used for secure data transmission. Let's delve a little deeper. In RSA, the security of the system is based on the difficulty of factoring large composite numbers. This is where prime numbers come in. 2 large primes are randomly selected and multiplied together to form a large composite number. This composite number is then used as part of the encryption key. The beauty of this system lies in the fact that while it's relatively easy to multiply 2 large prime numbers together, it's incredibly difficult to do the reverse. That is, to factor a large composite number into its prime components. This one-way function forms the basis of the RSA system's security. So, you might ask, why prime numbers? Why not just use any 2 numbers? Well, if we used composite numbers, it would be easier to factor the product, which would compromise the security of the system. It's the unique properties of prime numbers that make them perfect for this application. Now imagine you're a hacker trying to break into a system protected by RSA. You'd need to factor a large composite number into its prime components. Sounds simple, right? But with current computing power, it could take billions of years to do this for the large numbers used in RSA. That's longer than the age of the universe. This is why prime numbers are so important in cryptography. They provide a level of security that's virtually impossible to crack with current technology. But remember, as technology advances, so too must our cryptographic systems. This means continually finding larger and larger primes to keep our digital world secure. So prime numbers, while simple in concept, play a crucial role in securing our digital world. So, we have journeyed through the fascinating world of prime numbers. From their definition as natural numbers greater than 1 with only 2 positive divisors, to their unique decomposition in the fundamental theorem of arithmetic. We've sifted through the ancient Sieve of Eratosthenes and counted primes up to a given value with Chebyshev's pi function. We've marveled at the closeness of twin primes and pondered the unsolved conjecture of their infinite existence. We've charted the distribution of primes with the prime number theorem and explored the depths of unusual primes like Mersennes and Fermats. In the realm of cryptography, we've seen how primes serve as the bedrock for integer factorization algorithms like RSA. They may appear deceptively simple, yet they underpin some of the most complex structures in mathematics and computer science. Remember, prime numbers may seem simple, but they hold a universe of mathematical intrigue within them.